We are actually at the start time. Can I be heard?
Yes, sir.
Yes.
Great.
Morning.
Thank you.
Good morning.
Good morning to some, good afternoon to some, and good middle of the night to some. So I just have a couple of guests as unverified, which is fine. Not sure if we got everyone. I'll go through a couple of questions that came up to start with, but I'm missing one of the people that asked one of the questions, so I'm going to wait on that one. Okay, so you can see my screen here. One question that I was asked was to make sure that the files that we're using as examples are available. Basically, that was what the question was. In Oslo 101, we try very hard to make every file one that is actually shipped with Oslo. So here's the path to the demo triplet lens example, for example. And then there's another one for the doublet that we have. So that is just, you come in here and hit public, and then you can go to demo edu. And it's mainly this laser doublet lens, and then there's the demo triplet. Now, there is a point where we do some optimization, and we might send you those files from today. But yesterday there was nothing. So I'll make a note of that. If you follow along in the examples today that we're going to do, then you should be able to, you should not need to have those files sent, but it's nice to get them since not everybody has time to do those extra steps, and maybe you're doing your own work. Okay. So just a little bit more from yesterday on the interface. So the lens data spreadsheet, we're going to show a little bit on setup, wavelength, aperture radius, a little bit on these, I believe maybe a little bit more on the solves, and then a little bit on this special column. So setup, which is this button here in the surface data spreadsheet. Remember to open the surface data spreadsheet. You just need to click on this blue little lens, and it's right here within setup. Within this, we have, we're defining the light going into the system. Oslo doesn't work like Trace Pro. You define the beams of light going into the system. Someone else has shown up. I have to make sure to get those when I can. Hello. Hello. Okay, good.
I don't know why I'm disconnected every morning.
Oh, yeah. I managed to get you in. I have the meeting up a little bit better today than I did yesterday. Did you ask the beam splitter question yesterday? Not sure he's actually here. Whoops.
Yeah. Yes, I'm the guy that
Yes,
asked
you did.
yesterday.
Great.
Yes, sure.
Great. And actually, I was going to turn off my I'll do this first. I'm going to turn off my camera because, yeah, let me just make a comment. So I'm going to send examples. The files, I show the paths for them in this. Now, the beam splitter, I didn't find a good enough example. So my plan was to find a better example and follow up with the class on that, the whole class. The one that I did find was an interesting example that Dave Jacobson actually did. And if we go to open lens, we go to public, at the moment where I had put it was under demonstrations premium new. And it's this, and you could just go to your public directory and do a search with the operating system to get this as well, because it's called the, where is it? Micro reader aspheric system. But this isn't, I don't think this quite fits what you're looking for, because it does do a beam splitting operation, but it's not an actual Q beam splitter. It's just like it's a pellicle. So just the plane where we actually split. It does it in 2 configurations, and there's some other information. But this would take me a half an hour or 20 minutes to do correctly. So I'm going to follow up with the class on this specific question. The other thing is some of the tools that make this easier to do are actually in Oslo 102. Some non-sequential things and skipping surfaces and some more advanced things like that. So that's why it feels like it's hard to know how to do that yet, because unlike a solid modeling type of tool, Oslo is in this sequential mode, and you have to enter things in differently.
Yes,
so it takes a little bit.
I don't need it, but I don't need to treat it now. But can you just give me the name of the product, because I have a premium version, so I'm looking for in the public premium. Which one is it? Which lens?
Oh, which file?
The name of the lens file is?
It's demo premium micro reader _ aspheric _ system. But I might also follow up. I'll follow up with the whole class on the question.
Okay, I don't need it. If you can send me the file, it's very useful for me. Thank you very much.
Well, it's shipped with the program. You already have it.
Okay, I verified. Thank you.
Yeah, you have it under this, but don't worry, I'll follow up within a few days. So I'll take care of it. Okay, let's move on and get to the class. Back to the class. So the next, so the setup button allows us to set up light going into the system. So in these systems, you have to set up a field or a field of view. Field of view is often used when you're dealing with an angle, but field or field of view is often used. Sometimes you even use the size of the sensor and project it out into the object space. And then there's also the aperture, the stop, but really it relates to the stop in the system, but really what it is it tells us how fast the system is. So actually this little example has it. See, these cones have a certain width to them, a certain numerical aperture when it's finite conjugate. When it's infinite conjugate, we tend to work with something called F number. So this little button here, this setup button, I'm going to go back to my demo triplet example. If we hit this setup button, it allows us to enter in aperture and field information, and you can also set some conjugates. So you can actually set where's the object, where's the image, and a few things like that as well. Some of these are computed. Also, if I select one, I can't select both of the image height and the field angle with a defined system that's over specifying. So if I were to change this field angle, for example, to something like 16, you'll see it recalculates for the Gaussian image height. If you're doing more advanced sorts of things that don't follow paraxial optics, then it's a little more advanced, and you should be setting these targets up inside of the optimizer inside of an error function, for example, to set some of these initially or just manually set them. Oslo does not have that built into it, but it is also a much more complicated topic to do those kinds of systems that only have a plane of symmetry that aren't just cylinders, general freeforms and systems like that. I mentioned the conjugates aperture. Aperture divisions relates to an analysis thing, and I'm just going to show this. This is another thing that I don't think we have in the interface anywhere, and I've thought about putting it in. There's a way that Oslo samples in the error functions you define, but there's also one that a lot of the evaluation features, and what it does is it separates the pupil into a grid of some sort, and that's set with this spot diagram setting, SDAD. And SDAD can be set in a few places, but one of the most common would be the spot diagram. So I'm going to use my forced operator here, and we have spot diagram setting, and then you can see we have aperture divisions across the pupil. So if I set that more densely, I'm tracing more rays, sampling the pupil more densely. So if I have higher spatial frequency information, that's good. You don't always need to do that. You can see even at 17 across, it gives quite a dense set of sampling. So that's what that is. Gaussian apodization is for Gaussian beams, and it gives you a 1 over e squared spot size or radius. So that's if instead of assuming the pupil is uniformly illuminated with a radiance, it's illuminated with a Gaussian profile. Wavelengths and weights I've talked about a lot. Wavelengths and weights is within that surface data spreadsheet. So here, wavelength. And note there's a weight. Current just says which one's being evaluated. You can actually generate these as well, and you can change their weightings. And you can see this when we run certain analysis. You'll see we have the wavelengths and the weights. When we generate error functions, usually it only, if you change the weight later, you need to regenerate the error function. That's a general principle in Oslo, that just because you change a weight somewhere doesn't mean it changes it in the error function. Another quirk with wavelengths is we enter the middle wavelength and then low and then high, and then you alternate low and high. I'm not sure if it says that in the page. It might say that. The reason we do it that way is that is how the V numbers are calculated correctly. It doesn't break anything to not enter it that way correctly, unless you're optimizing and care and do things where you care about the Abbe numbers. If you don't care about the Abbe number, the order doesn't matter. Or I should say generally also partial dispersion. So the chromatic properties in terms of the definitions that we might use. So wavelength 1 is the center wavelength, 2 is the short, 3 is the long. If you have a monochromatic, just delete wavelengths 2 and 3, for example. Often people will use 5 or even 7 or 9 wavelengths. 5 is pretty common. 7 is very common also when you're doing more serious work nearer to production for systems that have, say visible wavelengths. But if you're doing very broadband, like visible through the near IR, you may have even more. And then Oslo lets you change which wavelength is current. It says here again, weights are specifically used for spot diagrams. Okay. Next up is apertures and checking. And apertures and checking, I mentioned checking before. When you check a surface, you put this little K here. I'll just show you how to do this. This surface here, this first surface, is checked. That simply means that if light is going to go outside of that boundary, it would get blocked if a ray goes outside that boundary. If you do not have checking on a surface, also will ignore the aperture size and just keep on tracing because it's just math. So this is very powerful to be able to ignore the aperture radius like that. But if you really want to tie it in for production, you might check the apertures. Just make sure that if light is going to get clipped by a surface and you're modeling it near the end when you're nearer to production, make sure to have the aperture checking on in the appropriate places. Often people will put it on for the aperture stop. The aperture stop, by the way, in Oslo, you have to actually size it if you're going to do that correctly to how you've defined the light coming in. Just a little bit of a warning. And we have some tools like beam footprints that help with that. And there's a whole set of videos in that we have, at least one video on that shows that. So we have a lot to support that. So that's what checking means. Checking doesn't affect everything. It doesn't, it affects ray traces, lens drawings, spot diagrams. It affects some kinds of optimizations, but not all kinds of optimization. So just be aware of that. When we do a pickup on apertures, it works like other pickups. When you do a solve, it essentially solves for the value of the paraxial marginal and the paraxial chief ray, meaning the formal chief ray at the edge of the field of view. In a sense, it's a little bit like a Delano diagram or a YY bar, where you're figuring out the first order of how big a surface needs to be. If you have distortion or other things in a system, though, it might be off from that value. So what I always do is when I get near to production, I always check how large are my lenses and do I have enough clearance for tooling and other things for fabricating the parts. But also gives you the footprints and all the tools to do this, as well as just these diagrams. So for example, this middle lens is not big enough. I would say I would want to make that one a little bit bigger for production. But for right now, it's not a check surface. It's no big deal. This is why it's nice to not have to worry about the apertures all the time. What the reference surface does is it allows you to change the surface that the rays are aimed at away from the stop. And there are a few cases where that can become more important. One is where the reference sphere is getting very curved. I'll talk more about reference spheres a little bit later. But when a reference sphere gets really curved and a ray would miss it, Oslo will start throwing errors at you. And so you can change the reference surface to try to help with those kinds of problems. Special aperture data allows you to define complex aperture shapes. What kind of complex aperture shapes? Well, early in James Webb Space Telescope, Oslo was one of the key tools, if not the key analysis tool being used on it, which is a testament to how well put together the program is. But part of that was because the apertures were done so well within Oslo. So this is actually a real strength of the program, that you can use elliptical, rectangular, triangular, and quadrangular. You can have transmit, obstruct, or pass-throughs. You can group them together, put them in a group, and you can put together some pretty sophisticated things. So here is an example of an aperture that's set to special. If you notice, normally I just have, like here, it's not even solved. If I go to solve this, now there's an S here. If I go to check it, it's got a K. If I come here and put a special aperture on, I may just want to put an ellipse or something on here. I can punch in numbers here. And when that happens, when you do that, you'll end up with a little X here. And I actually have an example that I like to show in the class, just to show. I'm not going to pull it up. Here is where it's located. But there's this smiley lens. This is just a wavefront graph. So this is just, actually, why don't I just pull it up? It's quick. Here's the smiley lens. So I pull it up there. If I just hit this, I need the single wavefront. So here I'm going to switch to wavefront, and I'm just going to do a single field point, which is on axis. I right click, and I'm going to increase the number of samples in it. You see now it looks a little bit smoother, not quite as smooth as what I have in the notes. And what is this thing? Well, if I open up the special aperture data, it's a set of ellipses and a couple of triangles, and they're shifted in different positions. So I got a couple of ellipses here, which essentially are circles in this case. And then I have a triangle set here and a couple more ellipses down, I believe, to make this smiley face at the bottom. So you can make quite complex apertures by doing this. And you have to be careful. Here I have one as an obstruct and I have ones as transmit. So one of them is probably the top of the smiley face, another one's the bottom. So you could play around with that. There's some other aperture examples in Oslo in the same folder, I believe. Yes, it's just there's an apertures file here, public lens elements aperture. So these are aperture examples. Okay, just a little bit on coordinates. We do a lot more in 102, but there's a few important things to say. There's a very nice section in the, I believe it's the optics reference has this, but look up the coordinates in our documentation. Inside these programs, we set things up with local coordinates. You can do global. In local coordinates, we use Euler angles, which is a tilt about the X, Y, and Z axes. The Z axis, in our case, let me go back to a real lens here. So in this lens, the Z axis points to the right, Y points up. That means X is going into the screen. You can also do some 3D sorts of perspectives if you want to get a different look at how the lens looks. Now, there are many different things that we have in our coordinates. You can do coordinate returns. You can do like a goniometer and pivot about a point that's not at the vertex of a surface. In other words, I can actually pick a point in a lens like here, and I can tilt a lens or a surface about that. And then you can reverse order of operations, and you can do quite a bit with this. Another nice thing with Oslo is oftentimes we can do things with less numbers of surfaces than it would take if we did not have all of these options. The negative of it is I guarantee you, if you're right before your review and you're trying to set your coordinates up and it's something tricky, give yourself enough time because the first time I set things up, it sometimes takes a little bit of trial and error, setting up some bigger numbers, making sure things work the way they do, especially if you're starting to do things in and out of the plane. Trace Pro is more like a CAD tool, and I think is nicer this way. And of course, your real proper mechanical CAD tools are sort of the kings at this, or queens at doing this sort of thing. And so there's a base coordinate, and then you can alter these coordinates. Now there is one point I want to make, and this is stated in the documentation. TLA and TLB about the X and Y are left-handed. Why? I don't know. And an older, no longer with us, optical person, Kevin Thompson, and I, who he worked on different design codes, tried to figure this out at one point, and I'm not sure either one of us really figured it out. But for some reason, those are left-handed. So if you don't like that, all you have to do is just change the sign from the right-handed convention, and you're good to go. That's all you have to change, but it's annoying. So just remember to flip that sign. Those are left-handed. Just a quick re-emphasis on solves. They're used for a ton of different purposes. Curvature by ray angle, so you can constrain the numerical aperture with that, for example. With thickness, you can set the praxial image plane with that. Let me just show those two. I'm not going to... Actually, I'll show a real quick example. So I'm going to just hit here PXS. And you see this image axial ray slope, and you see how it's B1? So I'm going to come in here, and I'm just going to set a solve to the axial ray angle, and I'm going to set it to B1. And it stated exactly the same value that it was before. But now it's constrained. So if I change something else, like if I make this 18.5, it was 19.3, watch what happens to surface 6's curvature. See how it changed? It changed because it was constraining to keep the same axial image ray slope. And if I hit the paraxial setup here, it kept that fixed. What it did was it kept the speed of the lens the same by changing this last curvature. That essentially, in this particular example, kept the focal length the same. So solves are useful for that. Another common use of a solve I've already shown is setting the paraxial image plane. So there we can set the paraxial image plane. But of course, in this lens, that's not the best for the imagery. And then another example of solves, as mentioned earlier, is you can set the approximate size, the first order marginal ray and chief ray for the system height or aperture radius. Notice one funny quirk in the language here is we have radius of curvature and then aperture radius. Aperture radius just means the semi-diameter, so half of the diameter. Okay, so we're going to open the demo triplet now. From scratch, which essentially I've got it open now from scratch. Show the lens performance with the report ray intercept curves. That's this button. Change the wavelength to E, F prime, and C prime, and it says what wavelength order is correct. It turns out if I want to change those wavelengths, I can just come in here. Now, if I happen to remember E, F prime, C prime, great. 546.1, 480, and I can't even remember the other one. They're slightly blue shifted. A lot of designers do like to use those. But notice right here, we do have some handy spectral lines already defined. So E would be the middle, F prime would be the low. So we go here, this cadmium line. And then C prime, which is up here, that's actually another cadmium line. So there you go. When we do this, that's the wavelength order. Now it says performed a spot size autofocus. So that's where we come down to here. And this is another type of solve. Spot size, field average, polychromatic is what we'll do. And so it wants to shift it 17.8 micrometers is how far that wants to shift. Now I know this is in millimeters because my general is in millimeters. So you get pretty used to just multiplying by 1,000 and calling that in microns when numbers are small like this. Okay, so let's see, field average. We're ignoring changing vignetting, the current graphics window. I didn't have it on the old one, but if we change it here, it would have been slightly different with the older wavelengths. I could go back and change that in a moment if we really want to. No, one thing I can do here is I can actually, I think I can lock this. Or is there a way? I think if you right click, yes, I can lock that window. So this window is now locked. I can't actually update it. So that's a trick if you want to keep something locked. Didn't show that earlier. Lots of little things like that that are useful within our interface. And so did this ray intercept curve for this one. Let's do it for the original case. So I'm going to have to unlock this window. That's all right. Oh yeah, I've got a right click. You can tell I don't do that very much. So now I'm just going to go X out of this. So that goes back to before we made those changes and do the ray intercept curves. And you can see it really doesn't make much of a difference at all. There's a small amount of difference in the color. And if you look really carefully, you might notice some small differences. Look at this curving a little bit more in the astigmatism originally versus that other design. Although, oh no, look, got to be careful. Sorry, I know it's a little hard to see this. The scales are different. Now, if I wanted to look at them on the same scale, I could right click and you can actually go in and change that scale of that plot, for example. And I right click there to zoom out because I don't want to update that graphic. I just updated this one again, double clicked, and it zoomed out automatically. So if you unclick all the apertures and update the graphics window, this is a good time. As you expect, this thing is, even though we're drawing a subset of the rays, when I uncheck these surfaces, it's going to let a lot more light through in that grid that I showed you earlier that we have. So we're going to not check and not check. So you can tell right here that we are clipping light as we go out in the field of view because these fans are being clipped. These are plots of where a ray is in the pupil versus where it goes in the image plane. So when we're clipping these at the sides, we're essentially clipping off parts of the pupil. Well, when we don't do that, notice the performance is a lot worse towards the edges of this, as you would expect. The scale doubled here. If I wanted to do it in 0.1 units, I could just change this to 0.1. Showing you some things that later on are pretty universal for evaluation. Okay, what about the Hubble Space Telescope? It asks us to do the same thing. I did this for a reason, and that was to remind you that we just talked about we'll just go to this one. Again, the Hubble is in that demo, the lens demo edu file. And now if I come into here and I click on this, what happened to these rays in the middle? Well, we have this central obscuration. So not only do you have the secondary mirror that would block things, but we also have a hole in the primary to get the light through on the back end. This is a traditional telescope design that not one of these 3-mirror anastigmats or one of these ones where you try to not have the obscuration, where you have a little metering structure and some other stuff like 3 little fingers that'll hold this secondary mirror or some way of holding it, because I have to have a big hole to get this light in to begin with. Actually, Oslo EDU is pretty popular with amateur telescope people. We have a lot of people that do get on and use it. So that's why there's a hole. And then the other thing, just to show you here, is the apertures. So if you look here, we have a couple special apertures defined. So we have one that's just an ellipse. So this just defines that surface number 1. It gives us a hole in the middle. I believe it's oh no, this is just the incoming. So this is like an incoming port for the whole system. And then we have one here that actually blocks a lot of the light because it's an obstruct in the middle, as you can see, and it's on that first surface. Now, when we do that, we don't actually need to do anything with any of the other rays, because that gets rid of the ones that aren't going to get through. Okay, kind of interesting. So the Hubble, nice little example of that. Okay, on to the second session. I'm going to go through the variables and optimization a little faster than normal, because I think the example is really the way to do this. So variables. Variables are things that change in optimization. I already showed you can hit variable or special variable from this button. You can also go to the variable spreadsheet. And when you have something as a variable, you'll get a V. So this is the surface data spreadsheet. On the spreadsheet editor itself, it's nice to do this and show. On the spreadsheet editor itself, when we go to variables, you'll see we can right click and do lots of things we normally do. You have surface number. Configuration is if you have multiple configurations, you would use 0 for all of them, or put 1, 2, 3, 4, whatever configuration number for that variable. And there's a certain type that you can actually choose right now. And then there's a way to do constraints, minimum and maximum. Damping just affects the damp least squares. So, and there's a lot of different little fancy things. One thing that I'm going to show, though, is notice if I want to do an A-sphere, I could do a conic constant, but if I want something like a 4th order polynomial A-sphere, very common, I can't do it. And what you have to do, actually I'm on the Hubble, maybe it would have let me, I can't actually do it unless I actually define the surface as an A-sphere first. So the trick I do is this. I set some aspheric, and then I put some 1e to the minus 18, 20, let's say. So it's basically 0. I did a minus 120. Okay. So it's basically 0. Now, if I come back to the variables, I did that on surface 1. If I look for surface 1, now I can define AS1 or AS2. AS2 is the 4th order, or maybe it's AS3. Anyway, I could do AS2. Yes, it was AS2. But if I try for surface 2 to do the same thing, So now I try for surface 2, and I try to do the same thing, AS2. It won't let me do it because I haven't defined it as an A-sphere. So if you don't see the choice or can't type in the choice of a variable, just define the surface that way, and then you can actually even set this. Now I set it to a 0 again like it was. It's still defined as an A-sphere. It just doesn't have an aspheric value. Okay, that's what this bottom thing is. I believe we've got a tip that's actually on that. And it's also, I think we have a video where I show an overview of some optimization that does that. Field points are used in the surface spread, the spot diagram spreadsheet. And it's also used when we define error functions. So used for evaluation and optimization. It's independent from the drawing object points. Remember, those are under the operating conditions for the drawings. The basic data, again, it's fractional coordinates. There is a basic setting that gives you an FBY. Notice in Oslo, when it's pupil, it's FY or FX. And when it's object, it's FBY or FBX. Another weird thing in Oslo is that FBY is defined first because usually we're going along the y-axis when we define field of view. In math, we usually write X then Y, but in Oslo, it's Y then X. I wish they didn't do stuff like this. It's the way it is now. So we try to get used to it. Not a choice I would have made, but you do get used to it. Just be a little bit careful when you're first using it, that to go up in the Y, you recognize that that's the first one. So when you go to advanced, you can not only set FBY and FBX, but there's also an FBZ. So you can actually have field points that shift off in the direction of the axis, or if you have things that are tilted or other kinds of objects like that. The reference ones I'm going to skip, but those are more advanced. And then you have pupil coordinates, FY and FX. Those are telling you the extent that that ray bundle is defined if it's vignetted. So in our triplet example that I've been showing, those might be set to minus 0.4 and 0.4. If you are doing wide angle ray mode, you may not want to bother with that. But if you are using just normal central reference ray, it's a way to define the beams that are getting through the system with just having to trace that central ray extremely accurately. And it's fast, really nice and fast. And then as your design progresses, you need to update those vignetting. Vignetting is a subject we do in Oslo 102, but you can update these to define your beams as you go. The other thing is Oslo uses a current field point concept. Remember earlier when I made a comment on smiley face here that I was going to do a wavefront map and it was just on axis. I can do that here for this system. That's just on axis. You see FBY 0, FBX 0, focus 0. If I go to recalculate, it doesn't in this particular one let me change the field point. You can change the field point with SOP is the command name. Set object point. And it's so critical. I want to spend a moment on it. SOP is equivalent to trace reference ray command, TRR, and there's certain functions that will, certain things you call that will have this set object point. So you can type in, if I want to set the object point to a different value, you can just type in S.1, SOP 0.2. There's places here, like if we go to single ray trace, you can see there's a set object point here. I can click on that. You see now it's set to 0.2. I can now do 0.4. And then if I redo this graphic, you will see now it's going to 0.4. This, anything that where a calculation is done for a single field point, where you see a single field point like that, not like this graphic or not like MTF, are ones where we show multiple field points. If it's for a single field point, if you want to look at a different field point, you have to change the field point. Now, this isn't as bad as it sounds because one of the things you can do, oh, I'm not going to do it for that. I'm going to do it for this. Going back to the buffer here. I don't think that was the right one. Look looking for one that was that wavefront, and I can't remember the command for wavefront. Now we can come in here. Wavefront analysis isn't what I want. We want wavefront map, I believe. Remember I said I usually don't call things from here, and here I'm proving it. There we go, wavefront map. Now this one didn't let me actually change the field point in it, but I can hit map here, and did it actually give me the command in the buffer? Yes, PWF, that's right. I should have known that. Should have known. Didn't know. I hit escape there, by the way, when I was where I didn't want to be. But I can do something like this. I can do set object point, 0.8, PWF, there, and I did that one. You could even set up a few windows and string together a change in SOP along with that command, or you could write your own little routine that does it if you're doing something over and over and over again, and you need to be changing the field point. But it needed to make sure that you understood the current field point concept. Talked a little bit about these, that some vary with zoom position. Some apertures actually will vary with the vignetting. There's the aperture set and vig commands, which is done in 102 that I've talked about a little bit. And drawing points are not evaluation field points. So I've also noticed over time, sometimes, especially when I work with, I've worked with a designer named Elvis Patensky for years. He's not quite as careful at cleaning out field points. Sometimes you'll get some extra ones in there that aren't being used. And if they're not in the error function, they're not really being used for anything, I just go in and clean them out sometimes. Also usually cleans up after itself. That's just an area where it doesn't quite always do it, because it doesn't want to tell a user that just because you regenerated an error function or something, you no longer care about that field point. So along with the field point, there's actually also something called array set. I typed in that one little command earlier. I'm going to do it right here. GRST. And in the GRST, you can see I have some field points defined here. I'm going to make this window a lot bigger because that's just too darn small. And I'm also going to invert it. So it's a little, I didn't like that either. That blue is just not easy to see. So you can see here these little graphics are there. So you can see that we have field points defined down here for 1, 2, and 3. But the ray set is how we're going through the pupil when we have other things that we are, like say, an optimization. Optimization operands will sometimes ask, some will ask for a field point, and also where does it go through the pupil. So if I'm going to trace a single ray, it's going to say, great, where are you in the field? Oh, and where do you want to go through the pupil in that? So I need to actually, for some things, define a ray set, especially for optimization. So that's here under the ray set. Or RSE is the command. You can also hit the question mark here, and you can see optimize error function tables ray set, or RSE. You can define rays to be ones that are traced as reference rays, or ones that are just ordinary rays, which means it doesn't specifically try to iteratively nail exactly where you are and aim it exactly where you are in the pupil. And here are the coordinates, fx and fy, and a weight that goes with that. So similar sorts of stuff. Let's just define a few here. And let's see what happens. Let's go 0.3. And once I set that, I can actually, let's do minus 0.9. Whoops. Minus 0.9. And then let's just do, let's do minus 1.1 and see what happens. Oh, look at that. It accepted it. It turns out in Oslo, you can also define rays that are larger than the field of view or outside of the pupil. And there's cases where we might want to do that to make sure, for example, that there's some edge thickness on a lens. So there are cases where we might want to do that. So it does let you do that. Now, if we go here, and it turns out GRST doesn't update. Might be something someday to put in, but it's not too hard. Sort of a funny little command. GRST. Just made a note of that. Okay. And if you notice here, it actually has plotted these 2 points out, 1 and 2. So these are used in optimization. They can be assigned to any field point. You can pair them with different field points in when we define our error functions. And these are also ones that aren't always cleaned up, so occasionally you might want to clean them up. And here I tried to put a little show you where it is in the interface. Here's the help page for this, because I know this is really fast. You could just type in RaySet into the search, even see it in the index. But here, if you actually go to the contents and you go under optimization, data tables, you see here's the field points, here's the RaySet, here's the spot diagram set. This is that GRST command that I've shown a few times with some rays shown. So now we're going to actually switch our example to this laser doublet lens. So let me first just do a little bit of cleanup. I can tile my windows again. Nice and tiled. Now let's go to our laser doublet lens. So here's the laser doublet lens. It's really good performance. So here's showing the lens. Here's the report graphic. This is step 1. Make all the curvatures variables using the surface data spreadsheet. Okay, so I can make this a curvature, and I can make it a variable, and I can make it a variable, and a variable. So all my curvatures are now variables. Yay. Now, it turns out if you go into the variable spreadsheet, let's actually go to direct spec this one. You can click on this variables button up here, or you can actually make this a special variable. I come into here. If I want to do thicknesses, I can just hit vary all thicknesses. And that actually makes all thicknesses variables now. And if we come back out here, you can see all these variables. Since I don't want to lose my work, I can hit the green check mark. This means it's not saved to the hard drive, but now if I mess something up, I X out, I don't have to redo those 2 steps because I've accepted those. It says add a 0.4 FBY fractional field point in the field point set. Okay, great. Optimize. Field point set is actually down here, or FSE. Oh, these are generate field points. Whoops, sorry. I'll get to that in a minute. I can't actually, this is always the problem I have. I can never remember where it is in the normal interface. So I'll show you in a second. I just know how to get to it fast. FSE. So let's see. Field point spreadsheet editor. Field points. Oh, it's DAY2. Not smart of me. Right here in the field points is a really good place to get to that. Okay, great. So now it's asking us to, got that somewhere I didn't like, add a 0.4 field point to it. Okay. Come back to our lens here. Come back to our field point set, and it says add a 0.4. So I can left click here on 2. I could add a row above, but I can right click here and insert before, and then I can just put a 0.4 in. Now I've got a 0.4 field point set in here. Update the graphics window and note the change. These field points often will actually print out here. You can override it by right clicking. You can define your own or do direct inputs and different things like that. Some graphics that do multiple field points allow you to do that. So it's added that in. It says open a second graphics window. We happen to have one open already. View the field and RaySet sampling with the GRST command. So now we go to GRST, and you can see we've got these field points defined, 4 of them, 1, 2, 3, 4. The one I just added was number 2. I did not need to put that in order. I just liked to put that one as field point number 2 to keep them in a cardinal order, in an order where I'm counting sort of low to high, or going from low to high. Then it says add a few rays. We've already done that step. If we were to go in here and add a few rays, I'm only going to add one. So error function tables, ray set. I'm just going to add one that's at 0.5 in FY. And now if we do GRST again, make sure that your active window is number 2. GRST. Now you can see this field 0.1 is right here. I'm sorry it's in red. It's really hard to see. I'm sure it's almost impossible for you. But there's a red cross here with a 1. Okay, and then as a great tip, mini spreadsheets have easy commands. This is where I mentioned a lot of these I've used. Surface data spreadsheet is LSE. We have field point FSE, ray set RSE. OSE will be for operands. Tolerancing is TSE, and so forth. So what is optimization? In optical design, optimization is where we have some variables, some degrees of freedom, and we have some function, an error function where we're measuring how good the system is. And almost all of the error function values we either target something or we look to minimize, although there are some ways to do MTF targets, which in that case you would look to be trying to make them larger, not smaller. But the problem is quite complex. This space is quite jagged. It's got many, many local minimum. Some are narrow, some are wide. Depends on where you are, and you have to try to traverse this space. The design starting point for most optimization is critical. We do have some local and global local optimization, and then global optimization, and a global search method to try to help with these problems. To see more generally on optimization, it's in the optics reference manual. So when you go to optimize, what do we need? Well, we need to have an error function defined. So we need to have how good or bad the system is. So there's a number of ways I'll show in a moment how to do this. Under optimize, we have a number of different generate error functions you can use. You can also define your own. We have some that are set up using CCL with these OCM operand sets, which have various various uses. And the way that the error function works is it's a weighted sum of squares approach. I believe in the optimization chapter in the optics reference, we actually talk about how the weighting is done and how it's a sum of squares. But it's this type of thing where you multiply the weight times the error function value, and then you end up dividing by sort of the sum of the weight squared. It's something like that. There is a little factor in this that I'm just going to point out. When we actually go to do optimization, if you have put, like here you can see there's a restriction on this thickness that only allows it to go from 100 micrometers up to 10,000 millimeters. Sorry about the change in units. It's easier to mention it that way. And so because we're doing that, if we actually try to go outside the bounds of this, what Oslo will do is it will put a penalty on the error function. So you'll have the calculation from the error function itself, and then there will be an extra value added onto it as a constraint violation. And I had a customer a few years ago send in a support ticket where they couldn't figure out the value of their error function, and it was because it had a constraint violation and they weren't incorporating that. If you want to know how hard does it penalize those, it doesn't show you here. Well, it turns out for each individual lens, there's also a set of optimization operating conditions. So I use my UOC question mark, and you can see there's optimization. Whoa, I hit the wrong one. I'll just do it. UOC OPT is optimization. And you'll see in here it says, here's some values for damping factors. There's where in the world is it? Weight of boundary violation conditions. So this really hits these boundary violations quite hard. as 1,000 is the weight. And it basically takes 1,000 times that, and I can't remember if it's times it squared or the weight is squared. I can't remember exactly how it does it. Or exactly what it is, but it's something like that. I think it's weight times that value squared. So when we optimize, so we set up our error function, we set up the variables, and then we optimize. So let's first talk about the error function. So there are optimization components. The optional one I put in here is vignetting factors. So vignetting factors, as I've said, these are things where your beam may not go all the way out to the plus or minus 1 stop like our triplet, where it's truncating out at further fields of view. So therefore, we want to cut those beams down. So under optimization components, you can see here, here's where vignetting analysis is. It's in a really funny place under analysis tools, illumination analysis. And that's just because the illumination is drastically affected if we're cutting off a lot of the beam mechanically with a part, a spacer or a lens, something, or a threaded part or something like that. So here under our error function tables, we have field point set, ray set, spot diagram set. I've talked about those 3 different components. The vignetting factors, I'm trying to remember, I think they're under support routines. Yes, vignetting factors. You can, vignetting analysis, set apertures. Again, this is done in Oslo 102, not 101, where we actually show how to use those. There's pretty good documentation on these, and we have some videos on in the same place as the ray aiming. So it's the number 2 out of the 3 folders we have right now for our videos. All right. So we don't need to have vignetting factors set. And then, of course, field point set, ray sets for the pupil, and then sometimes the spot diagram for certain things like wavefront error function components and MTF. If you don't have something defined in the spot diagram spreadsheet, Oslo will give you a message telling you need to have one. So here is the spot diagram set. Spot diagram set is SDE command or SDS for output. Optimize error function spot diagram set. Let's just go there. So I just show you what actually pops up. Optimize error function. Actually, where was it? It was, I usually just do SDE for this. Error function tables, that's right. Error function tables, spot diagram set. Here's a field point ray set. Here's the spot diagram set. So you see I can define a field point here, and then it asks you to define, I think, let's just do 1. Oops, 1. And then it gives an aperture division and some other things. I believe this is another quirk of the interface. Yes. Didn't like that for 0, but you can set wavelengths, number of wavelengths, etc. What this does is this gives you a field point that if you want to evaluate something like a wavefront error, you can do that now that you've defined the field point. It does the same thing for MTF. Those are the only uses. Those are the uses, the main uses for it. So it specifies field point, how much sampling do you want in the pupil, the first wavelength, and the number of wavelengths. So the operand spreadsheet itself, OPE gives you this output. And to do the operands spreadsheet, you go to optimize, and it's under optimize and operands. OPE just gives you the output. Right now, I don't have any operands. I haven't defined anything yet. Couple little notes. If you have ones that have underscores and you type in OPE, it doesn't print out. So if you have one you don't want to print out, you type in underscore. You can put ones in here on your own and give them 0 weight, for example, or you can give them weights yourself. So here, this error function is trying to keep the effective focal length equal to 50. And then this is a spot one portion of a spot diagram error function. I just know because it's the Y's are the ray locations, and it's calculating a spot with this average and RMS. So even if you set a zero weight, by the way, it will do a calculation for it so you can see. Sometimes I put things in here just to monitor them and have no weight on it. So what you could do is you can set operands. There are a number of different operands defined. So we get to the example. I'm going to stick to the notes on most of this. So we have, here's where you find the user-defined operands, and then here's the operand spreadsheet. There's an ability to do things like I can take, as you saw here, EFL minus 50. That means the target is going to be 50. It tries to make it 0, or it penalizes the error function. Remember, lower is better in error functions generally. So what I would do here is a component. I can have two things in here. I can't do EFL minus 50 times 2 or something like that. It can only do 2. So to cascade them together, I can use O1, O2, and I can use an operator like this. And I can't remember if we show an example of that. There's also ways to do lower than, greater than, and less than, and other things like that. There's a ton of different operands. I come to this page all the time. If you just go in and look up the operands, I sometimes type in operands themselves. There are a number of different things. These next two slides are extremely important, by the way, for setting up error functions, because this will explain the structure of our operands and what the different little notations mean. So if surfaces, first surface, second surface, wavelengths, if it's got a configuration, field point, rays, spot number for that spot diagram, and a frequency, because for things like MTF, I need a frequency of what that MTF value is. And these are all defined with numbers. And sometimes, like for things like the field point, what field point 1, 2, and 3 is going to dictate when I put field point 1, field point 2, field point 3, because those are integers that go back to the field point set. Here's our basic components. Here's an example of an error function thing that we put in with a less than. So we want y less than 12. So we're trying to keep array height less than 12. Now for y, that's actually a ray operand. So the first number is the field point. So that's field point 2. Ray number is 3. And then the next one's wavelength. So that's for wavelength 2. For surface 2, and it happens, this one's for the second configuration. Now if, let's say you don't have multiple configurations, you don't actually have to put that number 2 in. If you don't want to specify a wavelength that's not the default, which is 1, I don't have to put that one in. So I could have 232 here, and that would just be field point 2, ray 3, and wavelength number 2. Done, if I just had those 3. So you see we have system ones, which will have surfaces or surface ranges and configurations, paraxial ones asking for wavelength, surface and configuration, and so forth. Aberrations, general ray, ordinary rays, reference rays, those spot diagram ones that I mentioned, which can include, like MTF will want what spot diagram number are you asking for, what's the frequency, and then if there's a configuration. So it takes a little bit of time to get used to this, but it's really well organized and pretty well thought out and has been copied by other design programs in the past. There are a few other funny little ones. There's these OCM ones. What OCM does is that actually calls a function that's specified in the optimization operating conditions. I can't remember if we mentioned that or not. Here's where we show this. But before I get to that one, here is statistical operands, average and RMS. So what these two do is average says take the average of all of these and then take the RMS of it. So it operates on everything between these two. And it's pretty well documented in our help. Here's an example of, let's say I have two things that I don't want to actually calculate, that I'm just calculating. And then I want to, you see, I take OCM2 and OCM3, whatever they are, user 2, user 3. These are defined to be whatever is in that optimization operating condition, CCL. User 2, user 3, the underscores mean they won't print out when we do OPE. And then we take number 4, we want to print that out so we don't do an underscore. And then you can see we can take OCM4 divided by 2 for that one. And then for 4, we might give it a 0 weight and say, let's add these first 2 together. And then the one we actually care about, the calculation for the operand, is adding together 3, which is OCM4 divided by 2, plus 4, which is the sum of 2 and 3. So yes, it is a little bit of a nuisance to construct these when you start getting many of them, but you can do it. You can actually also open Oslo files within a text editor, and when you do that, you actually get, let me just show that. There's actually a whole structure to these that we don't get into too much in 101. But we can get into in 102. So here I've opened up a version of the laser doublet that has some optimization in it. And you can see everything in Oslo is just a set of commands. And here, this one has some variables defined, for example. So if I have something I want in one file and I don't want to go in and copy the rows, even if I'm using Shift-Enter, copy, and then paste somewhere, I could also, if I just learn the format and I'm careful, go into the text editor, make the change, and then open the file up or copy some parts in. And we do have users that use that quite a bit. Here I mentioned the CCL components like these OCMs. When you open the optimization operating conditions, UOC, OPT, or it is in optimization conditions here. When we open this up, you see it has the name of a function. I guess this is now using operas, and I have no idea why. That's actually a SCP one. That's why it's got the star in front of it. The one that I have in the notes here is a CCL one. If you use ECM, it'll actually even do DLLs, and that's the way to do things really fast, which I did in the I've done all the way back to the 1990s. It was working very well. So that's what this is when you have an OCM, it needs to go to that function, and that function needs to be in the private or the public directory, depending on what it is, whether you've defined it or whether we've defined it, and tells you what to calculate in that OCM. The negative of doing things with CCL is it does slow things down a little bit. Even though it's compiled code, it's not as good as fully compiled within Oslo. There are some ways to generate error functions, and I'm going to go through these quite fast. I'll show you where they are because it just takes a little bit of experience. So there's a singlet, one for a cemented doublet, an old Genie ray aberration one, the spot size and wavefront. Then there's one that does aberration. I think it's, yes, just aberration operands, and it just dumps them in there. And a few others. Okay, so where all these are defined is under optimization. The workhorse one is this spot size wavefront. Oh, the Genie one, it was also called Dave Gray's method, which was an interesting old method. Sometimes works, not for every system. So the also error function, this is the workhorse. If you come here, it evaluates the RMS spot size or wavefront. The sampling defaults are based on Greg Forbes's Gaussian quadrature sampling. There's a paper that he wrote on it that we have cited in our help. It uses a number of rings and spokes, and then it chooses where to sample in a weighted way that gets the maximum amount of accuracy that you can out, assuming a rotation symmetric system and normal normal aberrations that we would have in a system. You can do a lot of other things to it. Like, for example, if you have an error function, you just want to add to it, you can do that. You can do custom weightings. You can do square grids. If you don't have symmetry and you want to trace rays for both sides of the pupil and you can actually do that. That's good for tolerancing. You can choose to use all wavelengths, or you can use Conradi D-D chromatic operands. You can do some custom weighting for wavelengths. You can add distortion and edge thickness. This is for premium only. I'll just show all of this stuff. If you come in here to optimize, generate error function, spot size, wavefront, here's where all of these are defined. Gaussian means don't necessarily trace in the center and at the edge, whether it's the field point or the ray set. Rado means you make sure to get in the middle, and Lobato means make sure to get in the middle and at the edge when you do that. So quite a bit in here, but this is the workhorse way to generate an error function. Here is the, you can see where the help page is and that page that I just showed. Singlet error function corrects third order spherical at a paraxial focus. It only works for if the lens is set up exactly right. Curvature 1 and image thickness are variables. And it does an autofocus as well. So that one has limited use, as does the cemented doublet. This corrects spherical aberration and coma. It does an angle solve. So you can see here it's set up. You have to have it set up as a doublet. It does an angle solve here to hold. The EFL basically holds the marginal ray angle along with an entrance beam radius that is equivalent to constraining the speed of the system, the numerical aperture of the system. Variables, curvature 1 and 2 does a PY in the back, so pretty limited. The Genie one is based on, I don't even know when the Dave Gray paper was, 1990 maybe. So he had an error function that was really efficient. And we've got it documented within here. I think it may be an SPIE paper. I can't remember. I haven't actually popped into it in a long time. The idea behind it was to try to get maximum amount out of each of the aberrations to, in a sense, do this in a way where the individual components of the error function are independent of each other. And it has some uses. There have been systems like I've had zoom lens designers say that they can't really use this. So you could try it, see if it works in your system. We've just never removed it because there are some users who do use it, a few that have even quite sworn by it for the systems they're doing. Aberration operands, I mentioned, it sets up, I showed when I clicked on it, it just popped them all in. It's 21 first, third, and fifth order operands. You can delete the unwanted ones you want, or just set the weights equal to 0. They are actually calculated in OCMs, and it's in this optimization callbacks CCL. And just to show you one time, to show that we've done it in 101, if you're like, I don't know what that is, I'll tell you I don't know either, necessarily right off the bat. So what I did is I opened up that our default editor. I could also be using Notepad++, which has some advantages. And if I go here to public, and now we look for optimization callbacks, optim callbacks. So this is a callback to a default function that we've defined. And so you can see right up here, OPCB_ABS. This is actually what this little command is doing. So that's the aberration one. I mentioned the Ray OCM operands. Actually, I didn't mention this too much. This is an error function on axis and one off axis field, gives you 21 off axis field points. Actually, slightly different than the other one that we had. Arguments are off axis field point, and the vignetting, delete operands you don't want. Again, if you want to know what that one is, it's in optimization callbacks. You can also generate field points independently of having to generate an entire error function if you want. So you can set field points automatically. You can use the different quadrature grid methods as well. So that is just here. So you can do a Oslo spot size wavefront and generate the field points there, or you can use a current field point set that you already had defined. And you can also generate field points with this field point set option down here. All right, we're now to the example. Oh boy. For some reason, I am really slow teaching this time. I apologize for that. So what we're going to do is I'm just going to go through this a little faster than normal. If needed, I can always record a version of doing this. But we've shown how to do all of this. So we're going to prepare the lens for the remainder of our sections. So here we're going to take the laser doublet lens, open it up. Laser doublet here, we've got it open. And what we're doing, we're just going to do a few quick things to it. We're going to save it in a new location. I've already done that. Change the name to laser double focusing lens. You just come up here and you put in whatever name you want. So I'm just going to change it to laser lens to make it fast. It says change the designer. So I'm going to change the designer to class here under designer. I hit Control Enter there instead of the green check mark, by the way. Change the entrance beam radius to 10 millimeters. So what we're going to do is we're going to make this 10 millimeters, which is actually making the problem easier than it was before, but we're going to give it a field of view now. So we're going to give it a field of view of 0.1, which means that if we go here, now we've got an enormous amount of coma coming in. Even though it's slower in terms of the beam not being the F number being higher, we now have a field of view. So that changes the system around quite a bit. Now, often I put a little field of view in every system because if you don't do that, it may be harder to align. Change the wavelength to 523. That's also going to make it harder. Right now we're at 632. So we're saying, let's say we have some magical laser at 523. No, I don't know what lasers are there. Make all the curvatures, thicknesses, and airspaces variables. So we go here to variables, vary all curvatures, vary all thicknesses, vary all airspaces. You can have a quick check through. You might want to put them in your own order or enter them in an order that you care about. You can also go into here and change the order of things. So there I did the reverse, which is kind of nice, but it's a little bit of a pain to do them in a drastically different order. You could also go in and just type and change around things the way you want. But this is good enough for now. It says put a paraxial image solve after the right after the second lens. So here's the second lens. We're going to put a solve on. Here's our paraxial image solve. So we've got that on. And then set the last thickness as a variable to allow it to refocus. So we're just going to make it a variable. By the way, when you make that one a variable, it doesn't constrain you on how large it can go. It assumes it's going to be a relatively small shift, which if we set it up this way, it is. And then we aren't using modern glasses in this. So let's get rid of that problem by do N-LASF 35. I went ahead and kept the same glass, but just use the green shot version of it. And then save the name with a new name after these alterations. I've already got a copy of it somewhere in case I screw up somewhere. No hints on that one. Now, we're going to do the next steps. So the next steps is when we're actually going to set it up for optimization. So setting it up for optimization. Here, first thing I say is review it with the report, ray intercept curves. Now we've gone from all that coma to a ton of spherical aberration because of additional changes that I made. The wavelength being a big part of that, and probably maybe the glass probably not so much, but we've also done a paraxial image solve, which didn't really change very much. Here you can see it's set to being in focus. It's just got a ton of spherical aberration. Not too big of a surprise. We actually come here and look. It's a lot of spherical. All the fields look the same. They're just all kind of mediocre, especially compared to the perfect lens we had before. And we should think we can get it back to that. It says create an Oslo, review the performance with the through frequency MTF. So this was step 2. Step 3 is create an Oslo default error function. Optimize, generate error function, spot size wavefront. I'm going to keep everything default. We don't have extra colors. I am going to switch to the wavefront here, though, so I do need to change that. Spot size tends to be better for systems farther from diffraction limited. This system's going to be quite good when we're done with it because it was quite good to begin with. And certainly review the different changes if you like. Now, if we hit OK, And then I come back here and let's just do a GRST. And you can see we've got certain sampling. If I come here and look at our operand set, we've defined a bunch of operands and we have our variables. We have all the elements now to optimize. Why don't we just do it? The answer is, if we do this, at the moment, we are not actually constraining the focal length or the numerical aperture in any sort of way. Focal length would do the numerical aperture. So we have to somehow constrain it. So we could use a solve on this surface for the marginal ray angle. We could actually even put a target to do that in our error function. But what we're going to do in this case is I'm just going to come into the optimize. I'm going to go to the operands, select this row with the left click. I'm going to do an insert before. And now I'm just going to do an EFL minus 60. And that is now constraining it to be a 60 EFL. Notice we were at 58.32, but I think the original lens probably was pretty close to 60. I'm not sure if it was or not, but here we're going to go ahead and try to pin it down at 60 millimeters. And that's a weight of 1. So now we can save this with a new name. Now, since I don't completely trust myself because I did it so fast, I'm actually going to go to my cheat lens, which is where I have all that set up. And actually, I'm not sure. Okay, so number 2 is the one that I've got that does part of them, and number 3 is the one that's set up to optimize. Okay. So this is just some hints of how to do all of these different sets. Okay, optimization methods. So we have, and the reason why we haven't optimized yet is because I haven't talked about the methods. So optimization methods. The workhorse is damp least squares. This is based on Nelder and Mead. I think is their name, 1944. No, Levenberg Marker, damp least square. Nelder and Mead is simplex. So simplex and Powell's method are in the program. Sometimes people get things to shift out of a certain space. You can see in numerical recipes what those are. Damp least squares is the main local optimizer. It basically measures a gradient and then takes a step size depending on how steep it sees it. But it has to do this over this complex space with many, many different variables. Then we also have a global optimization, adaptive simulated annealing, and then we have a global search called Global Explorer. Here's where our optimization algorithms are within the contents just under optimization, and you can read more about these things, about these different options. I've mentioned the operating conditions. When you pull them up, they give you the option to specify CLL or DLL routines. For damp least squares, it allows you to do things with the damping factor. And David Schaefer has done a lot with damping factor stuff within Oslo. And he changes the damping factor himself and makes changes. And I asked him once, do you think I could teach somebody who's just starting to do what you do? And he said he didn't think it was possible. Otherwise, I would have tried to have done it. And he would have told me more of what he does. Some of these designers can't quite tell you what they do. It's like in second nature. They've been doing it so long. He's been designing for 60 years. So we have the error function, and then we have weighting terms for damp least squares. There are some parameters for adaptive simulated annealing. It's basically how fast does it cool and at what point does it terminate. Then there's some miscellaneous ones in there. So again, just so you see exactly where it is, because the optimization operating conditions are good to know, even if you don't do much with them normally. Here is the optimization operating conditions with all of the different things. You can actually even put commands in for different field weightings and pupil weightings and other stuff that I didn't even mention. Give 0 weight to incalculable operands. That's useful if you have one that's blowing up on you, if it can't be calculated or there's a problem. So there's some funny little things in there that even I don't use very much, but they're in there. Here's the optimization conditions spreadsheet. Damp least squares is the gold standard for local optimization. It uses derivatives along with a step size. One thing I didn't show is inside of our error function is something that you can do that's worth showing. Mention something about Lagrange multipliers for constraints. Right now, all of these are set to be minimum. This mode, if I switch it to constraint, what it does is now it will use Lagrange multipliers to nail and make absolutely certain that one is satisfied, and then it will do the rest. So you have to make sure you have the degree of freedom available to do all your constraints. So if I have 5 constraint mode ones, I better have at least 5. I better have 5 variables at least. Otherwise, it minimizes the function to a set of constraints. The damping controls the stability. The problem with damp least squares is you can get stuck in the flatlands and it can stagnate. You got to get it out of there. So people sometimes put aberration targets in. Sometimes they flip things around. Sometimes they change something or another. The best way to do it is to try to keep the first order properties the same as you're making those changes, to keep things nice and stable and traverse the space versus drastically jumping somewhere else. One thing I haven't shown too is where this is called. So up here at the top, this is one of the only places I use this top on myself. You can generate error functions up here, which we were doing in the menu before, but you can actually also do this optimization. This is damp least squares. I also just use the ITE command, and you can use the forced prompt with that. And also here under iterate is another place where that is. So those are all damp least squares. Just quickly, simplex is where you don't need derivatives. It's slow and stable, good for simple problems. It's kind of like this amoeba where it sort of moves and shifts around. Included somewhat for curiosity, although people sometimes have gotten it to get them out of a flat land space for damp least squares too. Powell's method is also non-derivative. It finds these things called conjugate directions, slow and stable, and sometimes it works when damp least squares fails. Again, this is in numerical recipes. I actually haven't looked. There's probably versions describing these Powell's method and simplex online nowadays. I just happen to have a copy of the numerical recipes book. Okay, Global Explorer. This one, what it does is it's starting point dependent, and what it does is it does a global search and uses damp least squares and has an escape function. It's really fast, useful for getting out of local minima, but it generates a finite number of solutions, and the way it's implemented, it puts them into your private directory, and it always has the same set of names. So if you use this, it's going to do that. It also requires a specific CCL at the moment, so it will want to use that CCL. So you can't use CCL-based optimizations unless you somehow combine the two, which we haven't had anybody ask for. And the people that well, anybody that's doing that has figured out how to do it or has asked us. But it is really nice for getting out of local minimum. This is, in Japan, it was Ishiki's method. So adaptive simulated annealing, this is true global optimization. It does a multiple solution generator and uses a little bit of damp least squares. It is the most efficient true global method, but global optimization on complex problems is a very complicated space as we define it. And we talk about AI and things like this. Maybe it'll affect this field at some juncture, simpler problems possibly. But, you know, how do you know when to add a lens in or take a lens out and do certain things? There's a lot of know-how involved in this, including the engineering stuff. That's what it's about by Andrew Jones and Greg Forbes. Note that if the search space is too large, it will blow up on you. Sorry, I got to get rid of a cat. That sounded bad. I just meant I had to put her outside of the room. So this is developed by Andrew Jones and Greg Forbes. But if you have a search space that's too critical, this will hang Oslo. This will tie it up. So make sure to start with simple, smaller problems and expand outward from there and how big of a space you're searching, whether it's number of variables or how broad you make them. So if Oslo does save everything before you try to run it. And the space is defined, for those truly interested, Every single variable has to have a minimum and a maximum to define the space with ASA. You can't actually run it in the background. So you can be running versions of Oslo running this thing in the background, which is nice when it's set up right. There is another thing that's not really optimization, but we have sliders in here. So under demos, triplet bending, you can set this up and shift them around. Gives you some parameters to control and different elements can be chosen. There's some ways to customize this. Sliders can be nice if you're going to change one variable and you want to see how something's changing. You can actually custom do your own sliders as well. Whoops, it did not like something. Surface data spreadsheet is open. Close it is what it tells me. So demos, triplet bending. Do not save. Okay. So here, as we bend this around, you can see the aberrations are changing. So sliders can be useful for that. Here we have bending. You see thickness doesn't change them quite as fast. You can actually also change the element that you're doing this to and the step sizes. So the slider stuff, there's a few of them here under demos and tools. There's the triplet bending one as one example. And then there's another one. I can't remember if the spherical mirrors is actually a one that has sliders on it. Joe Howard at NASA used to go around doing sliders and fun little things with mirrors. Haven't seen him give that talk in a few years. Oh, here we go. Under optimize, there's slider wheel design where you can set up your own user configurable metrics that you can use, what surface and which items you can use for it. This just gives you more of an idea of all the different options that you can do for drawings, what you can vary. So these are the variable names. So this is decenters, these are the tilts, and these are tilts about arbitrary points, I believe, is TOX, TOY, 2Z. And you can have CCLs that you put in with this. So you can see there's quite a bit, if someone really wants to get into it, what they can do. Okay. Crash course in optimization. Damply squares, and the main ones are adaptive simulated annealing and Ashiki's method, global explorer. So I'm going to go back to this laser doublet 3. So this is theoretically where I last left us, where we have our variables set and we have our optimization setup or operands set. And so I'm actually going to click here. I've got a couple of metrics that I'm showing. I'm actually going to just clear this window down here because it's a little distracting. I believe this is actually our array set. I have echo on right now. I'm going to actually keep it on. I don't have to have it on. You see, even when I canceled it, told me I did that. Okay, so we're now going to optimize. After number 8, we're going to save it with a new name, step number 8 here. So we set our lens up. We're ready to go. And I just checked everything. So that was step number 1. I reviewed the performance, which is step number 2. Second window made it active as well. And so let's see. So the second graphics window, this MTF one, is the one that I've made active right now. I'm actually going to go, I can't remember what I did with this exactly, but I want to actually have the MTFs available. So I'm going to put them down here in number 4. So we open the surface data spreadsheet, and I have auto draw on here. Now, auto draw will actually update as we optimize, which is one nice thing about auto draw. And we're going to optimize. So I can hit IT, I can type in ITE with a number or just do ITE, and the default is 10. I can hit this ITE here, but I can also hit this button, which will just crank it for 50 iterations. So I'm going to go ahead and do that. I hit 50 iterations. If you notice, our little error function started off at 1.31, and it dropped down significantly, very, very appreciably. But notice the lenses are thick. Ugh, not good. Design codes will do this to us. I already know I don't like it. I'm not even going to look at the performance of it. You could look at the performance of it if you want, but this is where we use our X. So hit X to get out of here. And now I reopen it. So what we're going to do now is we're going to open the variable spreadsheet. And I have a couple of thicknesses in here. These ones at 0.5 to 100 are glasses. I'm going to maximize the thickness. These could be at 7.5. So I set each of those to 7.5 max. So if it starts trying to get thicker than that, it's going to get really hit hard by the optimizer and told, no, you're not going to get thicker. Because I like that change, I'm going to go ahead and hit my green check mark. So that's in case it doesn't work, I at least have that one saved. That's how I chose to do it here. Now we reopen the surface data spreadsheet, and now let's optimize. Now, I find it a little distracting sometimes to have an old optimization run in there if I'm doing this. So I right-clicked and got rid of that with my text window reset. TWR is the command for that if you are interested. Now we're going to optimize with 50 iterations. So I hit it, and notice now it's not jumping down and is quite as happy. I can hit it a few times and make sure, oh, look, it managed to get itself out of that flat. Oh, look at that. Now all of a sudden it's moved all the way out. So we managed to get it out of that space. And now let's just take a look. So we wanted to run this. I could have locked this window to be careful. I'm actually going to run it down here. Has it improved? Well, it was 50 micron scale here. Now it's 2 microns. And you can see when it starts looking all wiggly like this, we're balancing lower and higher order aberrations for these types of plots. In terms of MTF, looks perfect. So has lens improved? The answer is absolutely yes, it has. And then we save our result in yet another file. All right. So that was optimization. So please do that example, that little doublet example, if you're a little rusty or want to practice, because it's set up to be pretty straightforward in doing every single step, because this is a little bit of almost like baking almost. You have to set up certain ingredients to do an optimization. You have to do certain setup things to set up your lens initially. Now we're going to talk about evaluating performance. So there's a whole section in the help on evaluation. We do evaluation to get either output in the text window or the graphics window. We're going to look at both of them here. Output can be found with commands. I've shown you menu items, text to graphics, the windows, and the buttons. And I'm going to show just a very, very brief intro to tolerancing, just because if people only take 101, I should at least mention it, even though we do more in 102. So one type of analysis in optics, you'll hear about first order and third order analysis, or lower order, higher order, etc. Even for systems that don't have a plane of symmetry, there'll be first order and second order types of analysis. But we do assume some symmetry with our paraxial analysis here. We have paraxial constants, the PXC command. There's PXS is the one I prefer. This window actually doesn't have it pulled up because I just used the command. But let me just show you in here. Remember, I said it was nice to have these aberration ones on. It's so that I have access to this PXS. So here's PXS. So that is that command. And it just gives more numbers than PXC. PXC gives a subset of these numbers. I like having PXS because it's got more. There's also zoom setup, which is data for all zoom positions. So there is ZPXS is another one, which gives it if you have multiple configurations. And there's a really nice command that I mentioned here in the notes. That is another one that I haven't put in the interface because it's often used for zoom systems, but it's got more general use than that. It's called nodal points. What's great about this is you can type in NODP and specify a subset of surfaces and get information about it. It tells you power, focal length, the first and second nodal point, the front focal, and actually what's front focus, and then the back focus for the lens. So distance measured from the first physical surface, and then distance measured from the last physical group. So zoom lens designers need this stuff a lot. But even if you're doing a lens like this, let's say I want to know what the focal length is of this first lens. So that's 1 to 2. I could do one thing here where I come in and I actually put in, I open my operans sheet, insert before, and I could do EFL 1, 2. And I know that because I just happen to remember that for that system, it can give a range of surfaces. When you just do EFL, it does the effective focal length for all of the surfaces. That could just be EFL1. I don't want to actually have it affect the mirror function. I hit Control Enter there. And now if I hit my OPE down here, you'll see it actually gives me that effective focal length. That's a lot of work. I mean, I do that sometimes where I put a parameter in where I want to know something. So that's got a 44.15 millimeter focal length. But if I type in NODP, and I'm not sure what the arguments are, I believe it's just 1 and 2 and then 1. But NODP, first surface, 1. Last surface, it defaults to 4, which is all of them. I'm going to do 2. And now it says wavelength 1. You'll see 44.1544. It matches what this focal length was up here. So NODP is just a fantastic command, even though it came from somebody who does zoom lenses. It's so useful for everyone. And I'm not saying a zoom lens designer can't do a fixed focal length. I'm just saying you don't have to do something that specialized to make that really useful. And then there's a way to calculate paraxial quantities. If I click on this paraxial constants, paraxial setup, you'll see it comes to this paraxial setup command. PSE is the command that does, and you can go and search through. So our hyperlinked pages really can be pretty useful for that. Paraxial setup from the surface data spreadsheet. So this is this. I don't know if that's where that actually is. No, not quite there. There's under evaluate, there's here it is, evaluate paraxial setup. Okay. Sorry, I got to write that down because I think that wasn't right in the. Sorry about that. I had to capture that in case that was not correct. I'll look later. Just a little thing I saw in the help. Okay, aberrations. It's under evaluate. It's also under that aberration button in the text window I showed. It allows you to calculate first order, third, fifth, seventh spherical, aberrations for how the pupil is aberrated, book till fifth order, and some other ones. It actually also we specify in the I believe it's in the general operating conditions what these mean, whether it's transverse, angular, unconverted. And there's even a wavefront one that you can do. We also have under the aberrations, Zernike coefficients, a little bit in Zoom group, and then this very specific Aldis theorem contributions stuff. So evaluation, this is aberration coefficients, all the different ones that you can calculate there. Here's where you come for help to see what these different ones are. The other ones, I'm just going here under the evaluation. I can't remember where that is. Yeah, okay, Aldis does it from there. The aberrations, evaluate aberration coefficients, apparently, yes, total surface contributions, the Aldis theorem being used there. So what are the surface contributions? So anyway, all of these are under the aberration coefficients, I believe. I just didn't quite see it there. Sorry, just a sec. Yeah. Here's how you do the zoom aberrations. Here's the other aberrations. Seidel, Zernike wavefront, total surface. That's the Aldous theorem one. Okay. The ray tracing commands, I've mentioned set object point, very important. Reference rays, if you need it to be exact in where it goes through the pupil, or Lagrangian is just a first order aiming at the entrance pupil method. And you can do that with, as I said, vignetting factors, for example, to get around any inaccuracy you think that might be hurting you with. Direct ray trace allows you to trace any arbitrary ray through a system, and you can put in some parameters to do that. And then there's a generic ray trace. And when I first started using programs like Oslo, I thought, when am I going to be tracing individual rays? I'm just going to define an error function and go for it. I find myself looking at where specific rays go on a pretty routine basis. Sometimes I just want to know the angle of a ray, maybe at a surface for a coating, maybe if I want to know how telecentric we are at the sensor, how perpendicular we are to the sensor and things like that. You can actually do block ray trace with an array set of arguments as well. So a lot of ray tracing commands. Here's where you can see them under the analysis tools. I mentioned the lens drawing operating conditions, which we've already covered, shows what's on the lens drawings. And so the lens drawing operating conditions, it's within the lens drawing. Now our drawings, this is actually something that Oslo is not up to date in terms of the current ISO 10110, for example. So we can do some drawings like that. When we're saying drawings here, we mean drawings within the program. So what our lens drawing conditions are and different choices for how many rays, front and back distances, and so on. We can have a plan view, a wireframe. Hidden line one's called a solid model. There's a really funny little one here that you can see it actually cuts out a quarter of the lens. You can actually even change that and have it cutting out less if you want, or a shaded one. Zoom drawing actually shows all positions. And I haven't shown this yet, but we have zoom. And here there's a couple, it actually will show all positions. Here we only have one defined. So let me just go really fast to just show something. Library, we'll go to Elvis Patinsky's stuff. I seem to pull up this Takanori Yamanashi design often for this. So there you can see, and this is actually drawn to where the image plane is lined up. So you can see where they all are relative to the image plane and how it's shifting. So this would be the sensor in this system. This design predates sensors, which is why it has such a big angle there and isn't a mobile lens, mobile phone. Evaluation setup. There's a number of different things we can do with evaluation. So if you go to the Oslo help overview and evaluation, or just here under evaluation, this tells you the general conditions, how to trace a reference ray or change the field point. Like I said, changing the current wavelength. And you can also change configuration if you have a multi-configuration system. I've mentioned the set object point, mentioned the changing the wavelength. And there's also a way to change the configuration. So remember, Oslo, you have to change the field point for certain things if you want to look at different, say, wavefront maps or point spread functions if you aren't plotting them all in with one big command. Mentioned the spot diagram conditions a little bit in the past, just the aperture divisions across the pupil. So here's the spot diagram conditions. There's some other goodies in here, like if we're defining the a spot size for a Gaussian optimized pupil. There was another place within the paraxial setup that actually did that too. This is equivalent to that or another place for it. You can actually show the area disk and spot diagrams. Diffraction efficiency, that's for things like if you have diffractive optical elements in it. This is just a physics command we set to switch over on how an internal calculation is done on MTFs. And then if we actually go, this is actually a fun one. I'll just show this. Sometimes these change when you change something in them. I don't want to use Yamanashi-san's lens for this. I'm going to go back to our handy dandy, wonderful laser doublet. So here's our nice laser doublet, really good performance. If I go here and I click here, now I do ULC SPD. Notice how it says 25. I could change that number here, which I will. Let's change it to 45. Hit OK. Now I come back here. I'm not sure if it'll do it. I need to actually regenerate it. So there, now it's at 45. But if I come in here and recalculate, and I change from 45, and I change it to 60, now this plot is showing 60. This is a case where now it's 60 in here. So you see it tries to keep that consistent. So if you go in and change the spatial frequency that you're looking at through focus MTF, it'll change it in that other place too. This is just that GRST shows that aperture divisions across pupil. Tons of different image evaluation stuff. To get to it, well, we have the menu and graphics windows. We have a lot of ray analysis, spot diagrams, wavefronts, point spread functions, MTFs. I've shown through frequency, through focus. We don't have two things. We don't have like kind of an Oslo 100 with some optics background or an optics class. Dave Jacobson and I are talking about that and how to do it, because if we do an optics 100 class, we're going to want to make something that works well with Trace Pro 2, or people can do one or the other or a combo of them. But I would kind of like to do that because I know some people haven't used a lot of these metrics. But read our optics reference for that and the online help. So here's where our image quality analysis is in the content section under evaluation. I'm going to end here just by showing a number of these different plots. And we've been looking at a lot of these. As time goes on, I still have 9 minutes, so we're actually okay. And we actually saw the tolerancing at the end. So, pardon me. So we have ray intercept curves. And this ray intercept plot is fantastic. It's got distortion. It's got how color is sort of color fringing, lateral color. It's got astigmatism, how curved are the fields. It's got a longitudinal spherical aberration, which is where the marginal ray is crossing the axis. It's got a chromatic focal shift. This one has some color correction because it's got a focus where 2 colors are corrected. It's an achromat, this triplet. And then we have these plots that show where a ray goes in the image plane relative to where it went through the pupil in X, which is on the left, and Y on the right. If a system doesn't have a symmetry, we would be tracing both sides of the Y, but you don't have to if it's got a rotational symmetry. There's so much in this plot. This is a great plot for designers. They get a lot of information really fast. Instead of doing rays where we're calculating where the rays go, we could also do this where we're looking at wavefront or optical path difference. So this is the same as the left plot, except instead of ray intercept curves, now these are, or transverse ray curves, these are now optical path difference or wavefront. Again, where are the rays going in the pupil relative to the sphere that it would be, the difference in where an ideal sphere would have it, which would be a perfect geometric image. We also have plots like there's a chromatic focal shift and chromatic lateral shift plots if you want to look at those specifically. Again, a lot of these, I'm giving you the names. If you type them in, might find them from there, but a lot of these are here under evaluate. Here's our spot diagram. Here's our wavefront. Here's our transfer function like MTF and that type of information, point spread functions. And there's also some energy distribution in circled and in squared energy types of things. Spot diagrams are a little difficult to get analysis if you're a designer and changing things. There's a recipolar plot option. There's ones that go through field and focus. If we just pop into Oslo real fast here, this, I'm going to actually get rid of, I'm going to turn that off. This is what, that's actually a wavefront one. Sorry about that. This is the spot one. So this is the spot one. And essentially, there's no color in this system. Another thing about this is, I believe there's a way to use X's on. Oh, you can show the area disk. That's nice. So how big are we relative to diffraction, the first zeros in the diffraction limited spot? There's no way on this plot to change to X's. On some of the other spot diagram ones, you can. So spot diagrams is the one where I like to invert background. Look at how much better that looks. Although maybe through the interweb, it doesn't look as good. Not as sure. So that spot diagrams, sometimes it can be hard to tell what's going on in a lens with that. With my example here, I can tell you this has a lot of coma in it because of how it kind of looks like a little bit of a glass, but also it's spreading out in this other direction, so it's astigmatic too, probably, and there's some color. We can also look at single spots. This is ones where you can use X's. And that one, for some of these also, I showed it in the menus, but here you can see that you also have ray analysis, which is a number of things, wavefront, spot diagram, point spread function, MTF, energy analysis. So these don't quite mimic, but they're similar to here in the evaluate. And then all these have commands. And to help learn that, we also have things like the echo and our help and the history buffer. Again, a lot of users never learn the commands. They just run something and then just run the command again this way, or cut and paste it, or even just dump it into a quick little SCP or CCL or something just to run, or even a text file with semicolons, and then just run their different commands after cutting and pasting. Lots of different ways people run Oslo. There's also ways to look at spot and optical path difference versus the field. Wavefront analysis. So this is basically comparing to if we had a perfect image, it would be a sphere. So we compare to that sphere. You can always argue about how much tilt or the radius of curvature. Radius of curvature will relate roughly to where the focus is, where we're putting our sensor in and out. So we have wavefront versus linear field. That's kind of the default one people look at a lot. So this is on axis, 0.7 field and full field. We also can do wavefront versus two-dimensional field. So here we have an X field and a Y field. That's useful for certain kinds of telescopes and things. We have a way to look at kind of one of these contour types of plots for this as well. I mean, this isn't a contour. This kind of at the top, some people would call that a contour. This is, I can't remember what this type of plot is often called. But one of these kind of height-looking maps, and here we have peaks. You can see the scale on it. And you can actually also even do an interferogram look at how many fringes you might get with interference between the reference sphere and that actual wavefront. So here's a PSF. So point spread functions, these are the impulse response for the system. And it would be the impulse response as if you had a star, a single point. So it's a delta function if you're thinking in linear systems. A lot of our systems aren't linear systems if they have a lot of aberration. But if it's pretty close to diffraction limited, it really does become like it becomes like the area disk if it's uniformly illuminated and a circular aperture. That's what you see here on this FFT-based one. So we have ones that actually are direct integration, which is an old method to do it, and I'm not exactly sure what it does. Pretty nice, accurate method. It's a little bit slower. And then there's FFT-based, which you have to do zero padding and other things with that. So there's your report here, which gives these plots as long as some scans, including some energy analysis. So this is a lot in the PSF report. Direct integration, and then the FFT are giving the same information. This is not the same plot. But if you do it for the same plot, theoretically, they should get the same results. And then you can even do the point spread function versus all fields if you have, moving in Y and also in an X field. We also have MTF. So this is basically measuring modulation, so peak and valley. And there's a function for how this is defined. So 1 is perfect. It perfectly replicates that spatial frequency. So most things are going to just drop off. I've been showing a lot of these. Even for a diffraction limited system, there's this diffraction limit. We also have MTF and phase transfer function versus frequency. We have versus field and through focus MTF. Mentioned that when we click that little button on the zoom lens analysis, we have zoom lens analyses. We also have text output for zoom lens stuff. And there's even more if you really dig in. There's some polarization stuff in squared energy. There's line spread functions, all the energy analysis stuff. And you can even look at MTF and field curve versus field. Okay, last thing, because I know we're right on the button at the moment, so I'll be just a minute or two more. So in tolerancing, I just want to show where it is in the program. So here with error functions and things defined, we can also do tolerancing. It's all here under tolerance. Here's where we define our different tolerance parameters. Here's where we can do a Monte Carlo simulation. Here's where we do sensitivity, inverse sensitivity, and other things. And then there's some older methods like change tables. So the goal when we do tolerancing is I can't make things perfectly to what I had in the design program to nominal. In practice, there's actually going to be some errors to account for in the system, and we want to bound those. And there's a lot of different parameters. Oslo has many defined here under tolerancing for grouping, as well as a number of different individual element or even individual surface things. And then we can do sensitivity, inverse sensitivity, change table, Monte Carlo simulation. So quite a bit of that's in there. This is just in case people don't go to Oslo 102. I like to mention that's where the tolerance stuff is. And here's our help page within the contents for that. Okay, so I didn't really have any exercises for the analysis, but because it depends on what you're doing. So feel free to look around at certainly at least the EDU demo library. And I showed the demo triplet a lot. There's also a Gaussian, a double Gauss lens that's inside of, I'll just show you where it is. Double Gauss lens is a historical form that was used for a lot of 35 millimeter format film cameras, which of course isn't now. In my public, go to demo, go to light. So I use this design a lot for other sorts of things. Look at different spot diagrams or different things with respect to that. So certainly try different things and try different evaluation and graphics. And we have, as I showed, our online resources and manuals. So we know that it takes some time to get used to using Oslo. I find usually most users within a few days, you're moving around the interface, no problem. And then I've tried to show the basic ingredients that you need to set things up and to do things like optimization. I've mentioned an idea for an optics class, but certainly if you're interested in additional training courses, please let us know and we'll work on that. We'll see what we can do. So that's it for Oslo 101. I know the evaluation was fast. Please look at the optics reference as well. So I'm still here. If there's any other questions as my action items following up to get you we'll get you the optimization laser doublet lenses. And then I'll also look to do that beam splitter problem as well. I think those were the two main ones I had, was the beam splitter and that. Are there any questions? Other questions? And note, it is still light outside here. And it's 9 o'clock at night. Okay. Not seeing any questions. So again, I'll also for the beam splitter question, since you did ask last night, there is some stuff in Oslo 102 that's helpful with it a little bit. I think there's a little bit more in depth on coordinates, which is a little helpful. And the other thing that 102 does is some non-sequential stuff, which can help with certain kinds of prisms and things. Beam splitters depends on what you're doing. And a little bit more, I believe there's a little more multi-configuration too. All of those are topics that are useful from 102. So, okay.
Thank you.
Okay, everyone. Thank you for your time. Hope you enjoyed the class.
Thank you.
Have a good
Yes.
day. Bye.
Please take care. Bye-bye.
Have a good night.